Okay, welcome back again, Annie, to another session of economics together. So today I'm going to be teaching a bit about isoquants, and we're going to look at a particular production function that looks like this.
Okay.
Okay, and what we would like to do is we would like to draw an isoquant, and we have a few steps to think about drawing this isoquant. The first thing that we would like to do is to show that it is negatively sloped. We would like to show that it's convex. It is convex. And finally, we want to show asymptotes. So we want to give equations of totes, right? Okay, so can you remind me what is an isoquant? So what do you think about when you think about an isoquant?
Absolutely. So in this setting, as I look at this equation that you've sketched here, I sort of like do a bit of a mindset change, if you will, where I switch from the idea of being a consumer and having different goods between which I have to choose to being a producer or a firm. And now what I have to choose between is different inputs that I can use to produce this output that I'm interested in. So am I right in thinking that an isoquant is this like producer equivalent of what an indifference curve is to a consumer?
Precisely, yeah, exactly right. So if you were to think about the capital here and the labor here as just being goods, right, then an isoquant will give us combination of capital and labor that give us the same level of output. Right?
Absolutely.
And if you want a bit of Greek, iso comes from the Greek, means same, and quant, what do you think quant means?
Well, I'm guessing quantity.
Quantity, yeah. So when I think of isoquant, I think of same quantity, right? I think of inputs and outputs, a combination of inputs that lead to the same level of output. Okay, now here's something that students kind of really dislike, and it's negative powers. Okay, so I see this production function. It might be a bit scary at first. So can we think a little bit about how would you go about rewriting this without negative powers?
Yeah, it's actually one of the first things I do, regardless of what I'd have to solve, so that I get a feel of what's going on. I'd write this as y is equal to 1 over the square root of this expression, which now will be a over k squared.
Excellent.
Plus b over l squared.
Excellent. So just to kind of see what you did there, right? This minus can be put in the denominator with a plus, and you just realize that powering something to a half is the same thing as taking the square root of that, right? And then you apply that again into the denominator. Okay, so let's get a feel a bit for this production function. What happens to the output? What happens to the output when k goes up?
Yeah, so it's just a few more steps than usual. It's not immediately obvious, but that's why I like to turn equations into this form so that I can understand the environment. As k goes up, this part of the internal expression a over k squared will go down since k shows up in the denominator.
That's right.
And then all of that squared still goes up, but since that's in the denominator of the big expression, if you will, y goes down.
Let's think about that one more time. Try that one more time.
Y goes up.
Y goes up, right? So because this goes up, this whole expression goes down. The square root expression goes down.
Yeah,
the whole y goes up.
Absolutely.
Yeah, very easy to confuse if you're not following that fairly closely. Okay, very good. So now we're getting the sense of okay, this looks like a production function. When I increase my one of my inputs,
so does my output.
So does my output. Okay, so now what does it mean for an isoquant or an indifference curve, if you like, because they're similar, to be negatively sloped?
Well, what I'm thinking about is that depending on which of these inputs I put on which axis, As I increase one of them, I have to decrease the other one to stay on the same level. And there's a couple ways to see this. If I want to see this graphically, we can get to that in a bit. But the way that I think is the most immediate one is about thinking about what you started the session with, saying that this is the same quantity. Yep. So if I know that this y is going to have to be a fixed level of output,
let's call it y bar.
Yeah, if I'm fixing my output to this constant level, y bar, I know that the expression on the right-hand side, namely y bar, it's a constant, it doesn't change. So now if I look at the left-hand side, and one of these inputs goes up, let's say k goes up, for the entire expression to stay the same, because I've just equated it to a constant, something will have to go down to compensate for that, if you will.
That's right.
And I know that a and b are parameters, so they're fixed numbers that won't change. So the only option for us to stay on the same isoquant, for us to stay on the same production level, is to bring L down.
That's right. So bringing L down means that this part of the expression goes up and counterbalances for those orange downward pressure, right? Because we know that the right-hand side cannot change, right?
Yeah.
So this intuitive explanation is enough, and it's formal enough. You could also use this in an exam to show that, well, when k goes up, L must go down. So there is a negative relationship. The slope of the indifference curve, if I move along the indifference curve, there's a negative relationship between k and L. Okay.
Absolutely, but an additional step to that would be to sort of still have a graph that shows how k and L are related graphically, so that we can observe in the x's that the first derivative is downward sloping.
Yeah, absolutely. So we could of course think about those isoquants, right? So we could first fix the x's to be k here. It's completely arbitrary. I could have had L there and L here, right? And kind of observe that what we're really trying to show is that it's both negatively sloped, right? So this, derivatives here, the slope of the indifference curve is downward sloping, okay? It's negatively sloped. But of course, trying to draw this ourselves, well, seems like a pretty nasty equation to try and draw precisely, right?
Yeah.
Or to sketch in any shape or form. So, okay, very good. So how could I do this formally? So in what we've learned in chapter 15, how could I do this formally now? Let's say that I'm not very happy with this intuitive kind of explanation, even though it's pretty solid. How could I do this formally?
Well, I can rely on what we relied on last session or the session before that, where we used the implicit differentiation formula.
That's right.
To try and understand what the first derivative of this expression is.
Okay, so remind me a little bit. So since I put k here on the y-axis and L on here, what we're really looking for is we're looking for the derivative of k with respect to L along this isoquant. So how would you go about doing that?
Yeah, so the formula for this would be minus, and then I'll have a fraction, in the numerator of which I'll have the partial derivative with respect to L.
Excellent. Partial derivative of what?
Of the entire expression, so y bar.
That's right. So, well, yeah, I can think of this as being some function y of both k and L.
Yeah,
right?
Absolutely.
So I'm going to take the derivative of the function y
with respect to L.
With respect to L.
And similarly in the denominator, but with respect to k.
Excellent. This with respect to k. And now, how would you go about solving this?
So this is where actually, like, thinking about how we started, I like to have the original production function that was given to me just alongside the one where I've gotten rid of the negative powers, because the two of them can be useful for different reasons.
Yeah.
So what I'll do is, like, for this case specifically, since I'm now taking a derivative, if I go back to the way that this production function was presented to me, the chain rule becomes a bit easier to use there.
That's right, yeah. So if you try to take a derivative of this, well, you'd have to use a quotient rule, and you'd have to use a chain rule. Might be a bit messy. We can still do it, but it'll be a bit messy. So in this particular case, it actually plays out. It pays off to just simply take the derivative of the original expression.
Exactly.
So let's remind ourselves how it looked like. Let's bring this implicit differentiation down here as well. So how would you do the numerator of this?
Let's see. I'll take the minus half in front.
Excellent, because we have here a chain rule, right?
Yeah.
We have a function within a function. So I'm going to take the derivative of the outer part first, right? So minus a half.
And then I'll leave the expression as is.
Yeah, in the bracket.
In the bracket. And what will change is its power. Well, by decreasing 1, I'm going to have minus 3/2 now.
That's right.
But then I'll have to still multiply it with the derivative of the inside expression from the bracket.
Exactly.
Which will now be minus 2b times L to the power of minus 3.
Minus 2b times L to the power of minus 3. Yes, excellent, right? And if I were to apply the same thing for the bottom part?
So here, symmetry of the production function really helps. And what I mean by that is that both K and L, except for their respective parameters, show up with the same powers and same exponentials everywhere. So it's going to be very much the mirror image of that.
Excellent.
But now with A, which is the parameter for capital, and just using capital instead of labor.
Yeah, excellent, very good. And now you can see why I didn't want to do double work and rewrite that bracket altogether, because I kind of anticipated that I could just cancel,
all of that cancels out.
cancel. What else can I cancel?
Let's see, the minus 2 will go, but then the parameters and the variables themselves, the inputs will stay.
Excellent. So now I have that my first derivative is simply equal to minus, well, I again don't like the minuses very much,
so swap them.
I can swap them. K to the third over AL to the third.
Absolutely.
Excellent. So, okay, so what do I know about the signs of K and the signs of L?
Well, just like with consumption, here we'll be focusing on the first quadrant on only like positive numbers for K and L because they're inputs. And I also know from the question that A and B are strictly positive parameters.
Right.
So both A, B, K, and L are all going to be positive numbers, which means that this expression is definitely negative.
Excellent. So we did quite a bit of work here to kind of show exactly the same thing that our intuition told us here. Right?
Absolutely, yeah.
Now we have a little bit more work, right? Here's the next bit of work. So we kind of showed that this is downward sloping like this, right? But we have to show that it's convex, that it doesn't look like this, right? So, the slope would still be downward sloping, but this would be a concave function, right? So we have to show that this isoquant looks convex like this. Let's think about the meaning of that, right? So what does it mean? What does it mean for mathematically for this isoquant to be convex?
So here's how I think about convexity and concavity. The idea is that the first derivative is telling me whether the slope is increasing or increasing at a faster or slower rate.
Yeah. And probably what you meant to say there is that when you take the first derivative, it's telling us the sign of the derivative, or it's telling whether the function is increasing or decreasing.
Yeah,
right?
Absolutely.
Yeah.
So when I think about convexity, I also graphically, this helps to structure it by seeing what's happening as the slope itself, as the first derivative itself changes along that isoquant.
That's right. I mean, when I think about a convex function, I really think of a smiley face like this, right?
Yeah.
And I think of this as being a convex function. And because it's a positive face, really what we're looking for is a positive second derivative, which in English, if I were to kind of, if I were to look at this for this particular question, what this would tell us is that the first derivative, right, increases as we move along the isoquant, as we move down.
Yeah, so along the horizontal axis.
Exactly, right? As we move down, then the first derivative will be increasing.
Okay.
Right? So that's what a positive second derivative, right? The first derivative is an increasing function, right? Okay, good. So how could I, and this is a bit more tricky, I have been given the first derivative, and I would like to show now whether this first derivative is concave or it is, well, whether the isoquant is concave or convex, right? So this is what I know at the moment. How can I make progress from here?
So like I said, we're trying to figure out how the first derivative is changing as we move along the horizontal axis in this graph of the isoquant.
Yeah, excellent. So let's draw a graph on isoquant. So let's say that this graph of the isoquant, we know that it's, if I put K here, if I put L here, we know that it's decreasing, right? But we don't know, it could be decreasing in a convex way, or it could be decreasing in a concave way, right? So how could we distinguish if we know the functional form of that first derivative? How could we distinguish between the blue isoquant and the orange isoquant?
So because we know this functional form, we can think about how both K and L, both these inputs here in this movement you're describing along the horizontal axis, turns out that despite the fact that they show in like different parts of the fraction, they have the exact same effect on the first derivative. And I can see now that you're getting ready to draw this rays that we've been using so much this last couple of sections, figuring out what the slope is of the first derivative in different parts. So if you draw a ray from the origin going through those new points you just labeled.
So let's kind of draw this ray here. Let's draw this ray here. Now, why are these rays important? Like what's something about this rays that gives us something about the first derivative?
So you'll notice that as K goes down, as you're moving along that blue isoquant, as K goes down, the first derivative decreases.
That's right. So here's one thing. If we are in the blue isoquant, right? I draw a tangent line at A. I draw a tangent line at B. What I notice is that slope becomes shallower, right? So the slope in absolute value decreases, right? It becomes less negative. So in some sense, it increases, right? Hence the positive second derivative, right? But what happens to the orange bit?
Well, it actually gets steeper.
Exactly, right? So it actually gets steeper. So that's exactly what we're going to use as the main way to tell us between whether this isoquant is concave or this isoquant is convex. Now, onto you. You know that the first derivative looks like this.
Yeah.
How could you tell whether you're in a blue or whether you are in the orange setting?
Yeah, so like I was saying earlier, as I go down that movement in the blue line, this change in K and L. So what is happening as I go down? K is going down and L is going up.
That's right. K is going down
and L is going up.
A is going up. That's right.
And both of these pushes go in the same direction. They both decrease the first derivative, which is a negative derivative.
Exactly. So this whole thing here, as I move along from point A to point B, this whole thing decreases.
Yeah.
So it becomes a less negative, which means the whole derivative is increasing.
Yes.
Strictly speaking, or if you want to look at just the absolute value, it is becoming shallower, and therefore it must be the blue line. That's right. My favorite way of seeing it with this rays is that actually this part here, right? The slope of the ray here, the slope of this ray here, because you have rise over run. So you could take the rise here up to from point 0 to point A, and then the run here. Well, the slope of that ray from the origin is simply going to be Ka over La. Right?
Yeah.
And that's actually showing right here. So as I move from point A to point B, this ratio here is decreasing, right? Or the first derivative is becoming less negative. And therefore, I have a little smiley face, right? So the second derivative, the first derivative increases as we move down along the isoquant, right? So as we make this movement from A to B.
Absolutely.
Good. Yeah, so let's do a bit of a recap so far. So we showed both intuitively and mathematically using our implicit function differentiation that it's negatively sloped. We showed that it's convex by looking at a convex shape and a concave shape. Now we have one more thing, which is we are asked for equations of asymptotes. And I always don't remember how to spell that, so I hope I've spelled that correctly.
It looks good to me.
It looks good to you? Good, I'm glad. So what is an asymptote, Amy? Like, how do you think about an asymptote? How would you describe to someone what an asymptote is?
Mathematically, I can think of asymptotes as the behavior of functions as one of the either inputs or variables is taking on more and more extreme values.
That's right.
And for those of us studying economics, that actually ties in pretty nicely with the asymptotics we do in econometrics, where that word also shows up whenever we look at limits of variables going to, say, infinity.
That's right.
Or to something that effectively is infinity, a very, very large number. So graphically, the way I think about that is trying to understand, since here we're in a two-input model, my reduction function only depends on capital and labor.
Yeah.
It's a matter of like seeing what happens to capital, for example, as labor takes on higher and higher values, and the other way around.
That's right. Yeah, exactly. So what we would like to know is we would ask ourselves exactly what you said. What happens to capital? Capital goes to where as L goes to infinity?
Yeah.
And equivalently, we could ask L goes to where as capital goes to infinity, right? Now let's think about that for a quick second. So if I look at this question here, and I'm looking at L going to infinity, what will happen to this expression? If L goes to infinity, what must happen to K?
So let's take it part by part like we did earlier. L going to the infinity. And for now, I'm going to focus strictly on inside the square root expression. Effectively means that this term B over L becomes 0.
Excellent. Right.
That goes to 0. So it means that I'm only left with A over K squared inside the square root expression, in which I can rewrite now that I don't have this plus in it. And I can express what we have here on the left-hand side strictly in terms of K.
That's right. So I can flip this, because I like to flip stuff around here. Square root of this divided by, I can split them up, square root of A like that.
Yeah. And now square root of K squared will just be K.
That's right. So I'm just going to have K here divided by square root of A.
It's going to be equal to y bar.
And this is still going to be equal to y bar. That exactly. Excellent. Yeah. So if you like, I can put a little star on this K, right? Because this K is a special K, right? Some sort of a special K.
Is the K that remains whenever L goes to infinity.
Exactly. So maybe a special name for that would be K min, right? Because it doesn't matter how much L you can get as many labors as you want. If you want to produce this certain level of output y bar, you're going to need that level of capital. It's non-negotiable, right? It's a minimum level of capital you're going to need
to produce this y bar.
Perfect. So then I can go and say K star min is simply going to be the square root of A times y bar. Okay. Now, if you apply the same principle and taking use of the symmetry of this problem, what can you say about L min?
There's going to be the square root of B times the same fixed level of output y star.
Exactly. And it's not very difficult. It's not very difficult for someone to be able to replicate this at home, right? So then let's put this stuff together for a second. What do we know? Well, we know that once I tell you a given level of output, well, you know that there's going to be some minimum K star, right? Let's make this a bit neater. So we're going to have a minimum level of K star or an asymptote, right? And the equation of this asymptote is simply that K will equal to square root of A times y bar. right?
Yeah.
And this is my K-min. And I also know that I'm going to have some L-min. And this L-min is simply square root of B times Y bar. Okay. And I actually know that this asymptotes, and then these asymptotes are functions of the output that I'm doing. So I know that I will never touch them. So I'll get closer and closer to those asymptotes, right? But I'll never touch them. And it's downward sloping and it's convex. So, you know, I'm not the best drawer, but should look something like that, right? As we go along, right? What will happen to these indifference curves if, for example, I want to put a higher output?
The isoquants, you mean?
Yeah.
We're now in a
exactly. Yeah. Thank you.
now in a firm setting.
We're now in a firm setting. That's right.
So you're trying to produce more and more output?
That's right. So let's say that this is, we can call this Y bar 1 and Y bar 1. And now I want to produce Y bar 2, which is higher.
Well, one of the first things we saw when we started off was that as we increase this combination of capital and labor, which is helping us produce a certain level, output will go up as well. So I don't see why this shouldn't shift up the same way that indifference curves shift up as we consume more and more. That's right. So the asymptotes will shift, right? So if I take this asymptotes here, right, these asymptotes are effectively going to shift out like this as I produce more more output. And can you tell me if you can? I claim that I've done this correctly, and I haven't. So I'm just going to move this up a little bit more. I claim that these kinks where the asymptotes meet are all going to be on the same line. So these are the kinks of the asymptotes. Well, doesn't this go back to what we were talking about last time in terms of homothetic utility and those types of functions? Okay, so it could go back to homothetic, but keep in mind that homothetic preferences was more to do with the fact of what happens to the slope of the indifference curve along a ray from the origin. To the kinks of these asymptotes. As opposed to the kinks to these asymptotes. So my claim is that it doesn't matter what your Y bar 2 is or anything of that sort. The kinks of your asymptotes are all going to be along that same dimension. Oh, I think where this is coming from. I think I know where this is coming from. It's the fact that in that intersection of those two asymptotes, so the thing we're calling a kink, I know that the slope of that will depend solely on these parameters A and B. Excellent. Exactly. And those parameters, by definition, they're parameters, they don't change, so that slope will be constant throughout. Exactly. That slope of the ray from the origin, from that, is just going to be rise over run, but rise over run is always going to be square root of A over square root of B, so that's not changing. So excellent. Yeah, very well done. So that's exactly what's happening over there. So if I wanted to draw the isoquant for this higher level, then I would, again, draw something that would look like this, where here now is some square root of A times Y2 bar. Exactly. Okay. Excellent. So that's it for today. So we went through isoquant. We practiced a bit more of an implicit differentiation. We looked at the idea of concavity and convexity. And now we are master drawers of this type of utility, of production functions. Absolutely. And we've switched into the firm setting, which makes things more interesting. Yeah, great. Well, up until next week, I'll see you later.